that's mathy. Dear Father, we excuse me. Thank you for this day, and thank you for these students. Just ask that you be with us today and help us to understand your creation a little bit more together, Lord. In your name I pray. Amen. I feel like I can't talk all of a sudden. I've been talking normally for about 5 minutes, haven't I? Somewhat. 10 minutes. Oh, okay. All right. So, moving along here, I want to talk about free and Noetherian modules, and I'm trying to talk about these somewhat briefly because I really want to get started on the modules over PID today. So I'm trying not to state proofs of things in here too much, or maybe at all. So you guys know that Noetherian was named after who? Yeah, Noether. Yeah, Emmy Noether, who was a very deep mathematician who was in some sense ahead of her time. And much of what we do in abstract algebra is in some sense influenced by her and her way of thinking, or her students. She died at a fairly early age after coming to the U.S. I think she was at Bryn Mawr College for about a year, and then she died from complications of a surgery or something when she was about my age. Yeah. But anyway, so this is theorem. And again, we're in, as I have mentioned, Advanced Linear Algebra by Stephen Roman, which is a good book. Of course, there's also good sections on this in Dummett and Foote, so after I'll try to make you a scan of what we're doing in here so you can look at it eventually when I find time. And but I would say that there's still lots to learn from reading Dummett and Foote, but I'm not following that because I find it to be suffocating because it has too much and it's hard for me to judge what I shouldn't cover. This, on the other hand, it's a good path. Let M be a free module over a commutative ring with identity. So what's that mean? What's this term free module mean? You guys remember from last time? Did I actually define it last time? Curses. Cardinality of a spanning set is greater than or equal to that of a basis. All right. Sorry. Trying to make sure I state it correctly here. So what's a basis? A subset beta of M is a basis if it's a linearly independent spanning set. Shocking. Sorry. And our module is, I made this was in the definition for basis. It's like the second sentence I wrote in the definition for basis. And our module is said to be free if M is equal to 0, or if M has a basis. If beta is a basis for M, we see that M is free on beta. I wrote that. I remember writing that. Right, yeah. So, this is encouraging. So it means that there is at least the case, there's the possibility that we have sort of a dimensionality result, right? I mean, if we're in the context of a free module and we're working over a commutative ring with 1, now that's saying a lot because not all modules are free, so it's not like as comforting as the thing we learned in linear algebra that every vector space has a basis, right? Which is to say that every vector space is a free module, right? Well, over the field, it is not a free module over the polynomial ring and its action by the a given endomorphism. Like VT is not free because it's pure torsion. And yet V as a F module is free because we can find a basis for it. I'm talking about V being a finite dimensional vector space. So context is important as usual. Now the proof here is actually quite interesting. So what he does is I'll sketch some of the elements of the proof, okay? Because I think they're interesting. But so he says, let's let I be a maximal ideal. Maximal ideal of the ring, right? He says that exists by theorem 0.23, which I will not be scanning, but you could find in your favorite abstract algebra book, right? The existence of maximal ideal. He says, so our first thought might be that M is a vector space over R mod I, right? Because R mod, let me call this thing J because I'll call it I, all right? There, R mod I vector space. Well, this is a field, right? Because a commutative ring mod a maximal, well, wait a minute. Is R mod I a field? Yes, it is a field. Sorry, I'm an idiot. A commutative ring mod a maximal ideal is a field. I was, for the moment, I was like doubting myself. Do I need to have that it's an integral domain? That's dumb. No. Just a commutative ring mod the maximal ideal. That's a field. That was one of our theorems that I tested you on. Yeah. And so he says, our first thought might be that M is a vector space over that. He said, but that's not the case. But we could look at a scalar multiplication like this, R plus I times V equals to RV. What's the trouble with that? What would that require? He says this is not well defined. Why is that? We would need what? We would need that we'd need that if R plus I was equal to R prime plus I, then that would imply what? That R V was equal to R prime V for all V and V, right? Well, I guess for all V and M, right? The V is from M, is it not? Yeah. But should that be true? I mean, he says that making this well defined, it requires IM equal to 0. Right, because, well, R minus R prime would be an I. Yeah. So that's not well defined, but you can fix it, right? What's the fix? He says fix by quotienting by what? Of course, the IM, which is, of course, linear combinations A1, V1 plus dot dot plus AN, VN. such that AI is an I and VI is an M. And he says, in fact, M mod IM is vector space over R mod I. All right. And then he shows that that vector space is well defined. The operations on it are well defined. The operations are probably what you'd. He says you have to show that the conditions R plus I equal to R prime plus I, and U plus IM equals to U prime plus IM. If those are the case, then it's what's the operation? The scalar multiplication on here is defined as follows: you take R plus I times U plus IM. How do we scalar multiply? You guys can tell me. This is my scalar. This is my vector. How do I multiply? RU plus IM. We have a winner. A minor. I don't even know what that is. But anyway, the point is, if you were to replace the R with R prime and the U with U prime, you should be able to show that we still get the same, that this scalar multiplication on this vector space is in fact well defined, and you can do that. The details are in fact in here. And then he says, okay, well, now consider a set beta, which is equal to bi such that I is an M. I is an M, listen to me. I is an I. All right. The corresponding set beta plus IM, bi plus IM, what's that? He says, well, that's a subset, of course, of what? Of M mod IM, right? I mean, it's IM cosets there. And he makes the following point. He says that if beta spans M over R, what was our notation for that? I think it was just this, right? Was it bracket, bracket? It was bracket, bracket, right? That was span, right? Over the ring. So if beta is a spanning set for M, then, what do you think the spanning of the beta plus IM is likewise a spanning set for our vector space, right? All right. And he has the calculation right there. And then he says, suppose that beta is a basis. He says then that beta plus IM is a basis for T mod IM. All right. And he has the argument in here. It's not that complicated, but I'll leave it out. He says, hence beta plus IM is linearly independent and therefore basis as desired. Okay, so we have taken the free module. So the existence of beta is given to us because we assume that M is a free module. We use that to construct a corresponding honest-to-goodness basis in the sense of linear algebra on this corresponding vector space, right? And then we can compare the cardinality of beta is equal to the cardinality of this beta plus IM thing. And he gives an argument to assure us that, the elements of, if we had beta I plus IM and beta K plus IM, it follows that beta I and the bi and bk rather are distinct, which is needed for that counting. I mean, essentially that counting follows once you prove that if I had two different bi's, if I had like a bi and a bj, and I put them equal, I mean, if I put them not equal, then it forces the bi and the bj not to be equal. That's the counting. So in other words, these are distinct. If those are distinct, there's as many of those as there are beta. There's an obvious bijection there, whether it's finite or infinite. So if beta is a basis, then the dimension, sorry about that. So the dimension as a vector space of this guy is equal to the, the number of, the cardinality of this thing, right? This modified basis, which is equal to the cardinality of the free the basis which M is free on. And then finally, he says if beta spans M over R, then beta plus IM spans M mod IM, and so the dimension, I jumped the gun somehow. Oh, sorry. Well, I'm sorry, there's something. Oh, it's the other thing, right? The cardinality of a spanning set is greater than or equal to. That's what I haven't proved yet. I mean, I haven't proved anything, but I haven't sketched the proof of that yet. Let's see here. So that, he says, if beta spans, forget that beta is a basis, right? So as beta spans, if beta spans M over R, then beta plus IM spans M mod IM, right? And so, and where's this and so coming from? The dimension over the field R mod I of M mod IM is less than or equal to the cardinality of beta plus IM, which, by the way, is equal to the cardinality of beta. Well, that's not, there's no longer equality here because we're not assuming it's a basis, right? So we've lost the assumption. Linear independence of the beta was necessary to argue these are distinct when you get into the details. So dropping that condition of linear independence, we lose the distinctness of these. And so I can't say that there's equality here. What can I say? See, because this could have more things than that if we don't have linear independence, so it's less than or equal to. But that's what we were trying to show in part 2, is that the cardinality of a spanning set is greater than or equal to that of a basis. Right? Because this anchors the dimension of a basis. This is fixed. The dimension of this particular vector space. So when I run into these kind of arguments when I was first studying modules, I was very disappointed. I was very disappointed. And the reason I was disappointed is because I really wanted, when I studied modules, for the dimension theory to be somehow more elegant and somehow detached from vector spaces. What I actually found when I actually dug into the details is essentially you take your abstract setting and you find a field and you take whatever you're working with and you find a corresponding vector space, steal things from dimension theory on vector spaces, and go back. Which is really annoying because I wanted something more. But it's all kind of what you've already learned before, just transported appropriately. I mean, yeah, it takes some imagination to create the vector space, like in this case, but there it is. Now, if the module's not free, these ideas are not there. These constructions don't pan out. All right, move along here. Again, I will get you guys a scan of this section so you can see the rest of the details that I haven't shown you. And I know I still owe you homework. I'm sorry about that. I'm sure I will give it to you entirely too late at a time of your inconvenience. Let's see here. Okay. Definition. What's the rank? The rank, which we denote RKM, of a non-zero free R module is the cardinality of any basis for M, right? And he says the rank of the trivial module is 0. By the way, I just erased some inequalities in that previous proof. What do those inequalities mean? I write something like bar beta, beta with bars around it is less than or equal to I plus, beta plus IM with bars around it. Oh, was it? Yes. Thank you. Yeah. What does that mean? Does it mean 2 is less than 3? Is that what that's about? What is meant by such an inequality?
Oh. So it means that you can form an injection from the set on the left to the set on the right.
Yes. That has to be an inequality understood in terms of the existence or non-existence of a bijection. Because or injection, yeah. How do we judge, right, injection is more to the point. But I mean, if we had a strict inequality, I would think that would mean that there doesn't exist a bijection, right? Two sets, like you can't find a bijection, for example, from the rational numbers to the real numbers because the cardinality of the real numbers is larger.
So strict inequality would be there is, yeah.
So those are inequalities about cardinals, which you may or may not have ever thought about before.
Yeah, no, I was thinking about this, like, when we talked about cardinality and real analysis at the beginning of the semester, we talked about the equivalence of cardinality and bijections, and so I was wondering, like, how you could extend that to inequalities using surjections, but it turns out so for surjections were the first thing that came to my mind, but it turns out that to show it using surjections, you need to use the axiom of choice, but to do it using injections, you actually don't. Which is interesting. But yeah, the proof.
So injections allow for indecision. So you're telling me. Here.
I still haven't fully understood the axiom.
Surjections require decision. I mean axiom choice, but interesting. I have not thought about these things that deeply. I just wanted to point out that is not an innocent little just inequality of numbers I just wrote. There's a lot packed into that. Because these things we just wrote are true for infinite dimensional vector spaces. Something I didn't prove in linear, but we could if we were, if we had the will of fire, is that dimension still makes sense for infinite dimensional vector space. We define dimension to be cardinality. And you can prove two different bases for an infinite dimensional vector space have the same cardinality. Yeah. Okay, anyway, moving along. There is a, this is interesting. So the thing I'm just skipping over is the thing I mentioned the last time, that if you're working over a non-commutative ring, by the way, this is for a commutative ring. Everything I'm writing today is for a commutative ring. What I'm about to say is for a non-commutative ring. The page I'm skipping, he gives an example of a non-commutative ring. And he says, let F be the vector space with a countably infinite basis, and let L of V be the endomorphisms over that vector space, the ring of linear operators on V. And he says, so L of V is not a commutative ring, since the composition of function is not commutative, of course. And he goes on to basically show that there's a basis of size n in there, where n is arbitrary. Anyway, page 130 when I get you the scan. I find this disturbing. But anyway, we're really more interested in the commutative case. Let's go on. Theorem 5.2. Let B be any set. And R a commutative ring with one. Tired of writing it. Then here's an interesting new thing. The set, check this out, guys. R upper B lower 0. Maybe you've seen this in reals, I don't know. R upper B lower 0 of all functions from B to R that have finite support is a free R module of rank cardinality of B. And the basis beta equal to Kronecker delta B. Well, that's he didn't say that, I said it. I said it. Where, how are we going to define delta B of x? What's that equal to? What does finite support? What does that term mean, guys? Little b is an element of B, I believe. I think this is the case. I mean, it must be because the rank of the basis is this, which is, I mean, that has to be the B has to be from B. What is finite support? Finite support means that these functions are what? What does that mean? I think so. Let me look it up so I can make sure we're right about that. I was thinking something else, but my mind is in a different world.
Yeah, that's what it means in probability theory.
Yeah, there we go. A function f has finite support if f of I equals to 0 for all but a finite number of I. So yeah.
So what is beta a basis of, and where are the delta b's?
This, all functions, this thing is the set of all functions. So we're saying that, yeah, delta b is a function. We're trying to define it right now. So the argument is that this thing is a free module, and that these delta functions defined the basis for it. There's two cases. And They're supposed to take the values in the ring. The only two numbers we have reliably in a ring are 1 and 0. I mean, the ring could be Z2, right? For example. Well, in that case, this gets stupider. To fold my cases on top of each other, something like that. So what should 1 if what? How about if x equals to b? And 0 if x is not equal to b, right? So you can prove that that is a basis for this, which then proves that that's a free module with rank the size of b. And then theorem 5.3, what's it say? It says that if M is an R module, B a basis for M, then M is isomorphic to what? This thing RB0. The set of functions from B to R with finite support. Oh, that's kind of neat. What this is saying is that this thing that theorem 5.2 just constructed is the abstract analog of like Fn. We always anchor all of our vector spaces. They're isomorphic to Fn. This is saying that if we have an R module that's free, it is isomorphic to the set of functions with finite support over the basis. So this is, in some sense, analogous of Fn for V over F. In fact, if we were to look, so, just to be more specific, in the case example, B is the set of numbers 1, 2, 3, n, right? And if we look at F, B, 0, right? This is the span of what? Delta 1, delta 2, delta n. So it's pretty obvious that there's an obvious isomorphism between this and what we usually call Fn, right? The isomorphism is just given by delta J corresponds to what? How you map a basis for my F upper B sub naught to my Fn, where F is a field. E sub j, right. I wish Zach was still here. I'd like to know if Zach, right? He was, yeah. If he was still here, I'd like to know if his intuition extends to modules. All right, at this point I'm going to read. So, two free modules over a commutative ring are isomorphic if and only if they have the same what do you think? This says that if we have a free module, it's isomorphic to this set of functions of finite support. So if they have another free module, it's isomorphic to its set of functions with finite support. And we know that the cardinality of two different bases is the same. So the cardinality of this thing is the same. So two free modules are going to be isomorphic if and only if they have the same rank. Okay. If we have if you have R as an integral domain, if R is an integral domain, and we have M free module over R, then all linearly independent sets have cardinality what? At most, rank M. And probably worthwhile to go through the proof of that. He says M is isomorphic to, this thing, right? So we need only, so it suffices to prove theorem for this, right? He says let Q be the field of quotients for R. I'm going to say field of fractions because I like that more. Same thing. Okay. We can do that because R is an integral domain, right? R being an integral domain, it has a field of fractions. And he says then Q, QK sub naught is vector space. All right, so again, functions with compact support from Q to R, or from K. Here K is the basis, I believe. All right. Well, anyway, he says if we have beta, what happened to my beta? It's horrible. There, beta equal to Vi such that I is an I, if that's a subset of RK not, well, that's a subset of, because the, no, I'm getting too rational. Q, words. This is a subset of that. So if we have a spanning set for the thing which is isomorphic to M, then what? Well, let's see here. If he says if that is linearly independent over Q as a subset of QK naught, then beta is clearly linearly independent over R, right? So he says this linearly independent over Q implies linearly independent over R by this identification up there. And then he says, conversely, suppose that beta is linearly independent over R. So that statement is much like if you have linear independence over the complexes, you have linear independence over the reals. But going the other direction, a little bit trickier. In fact, not true. I mean, we can have linear independence over the reals, but linear dependence over the complexes, I think. But here, it's not quite that. We have linear independence over R, and suppose R1 over S1. What did I say about not showing proofs today? plus rk over sk vik equal to 0. Suppose you have that. Where si is not 0 for each choice, and rj is not equal to 0 for some j. So these are all non-zero because the denominators are non-zero because these are supposed to be elements of Q. Just there exists r sub j not equal to 0 because we're supposing that there's a linear dependence non-trivially in the vector space, right? Then what do? Clear out the denominators, right? So you multiply by the S1, S2, sk, and what's that give us? Well, that implies that would produce a non-trivial linear dependence over R, which then implies that Ri is equal to 0 for I, but thus beta is linear dependent over R, if and only if it's linearly independent over Q. Anyway, I'm butchering it a little bit, but basically the argument here is form the field of fractions, study the correspondence between a linearly independent set in the original, RK0 module. And because there's a connection between linear independence or linear dependence of a set in there versus the set in the corresponding vector space, we just steal this stupid result from vector space theory again, right? All linear independent sets have cardinality at most the rank. We can't have linearly independent set with more. But this calculation is very much based on R being an integral domain because there's a step in here where you multiply by this linear combination of the field of fractions where you have to clear out the denominator. If R is not an integral domain, this construction is spoiled. And so we don't have this result more generally. If you're not working over an integral domain, you could in principle have linearly independent sets with a larger cardinality than your a given linearly independent spanning set. I don't know if that's true for a free module, though. I feel like we just proved, didn't we just prove that, we proved the rank of two different free modules was the same, right? So I'm not sure I entirely understand how theorem 5.5 is spoiled when we remove the condition of integral domain. Right, well, I'll think more about that. All right, well, let me just wrap it up here. Finally, the rest of this is devoted to considering Noetherian modules, discussing the ascending chain condition. And that basically is, a Noetherian ring is one which has the ascending chain condition. We talked about that in abstract a little bit, right? And theorem 5.7, this is the importance of Noetherian rings, theorem 5.7. And our module M is Noetherian if and only if every submodule of M is finitely generated. That's very nice. Finitely generated submodules. That's a nice thing. If you know that all your submodules are finitely generated, that's a fantastic thing to know. And that's something that you get if your base ring is Noetherian for the module. And he says, in particular, a ring R is Noetherian if and only if every ideal of R is finitely generated. So we may need to use this idea if we come up against, I think it may come up in the proofs in the next chapter, so we'll talk about it more there where it comes up. And then theorem 5.8 says R is Noetherian if and only if every finitely generated R module is Noetherian. Didn't I just say that? Let R be a commutative ring with identity. Is that different than what I just said? An R module M is Noetherian if and only if every submodule of M is finitely generated. R is Noetherian if and only if every finitely generated R module is Noetherian. Oh, not submodule, but every finitely generated R module is Noetherian. So in the wild world of modules, you can have finitely generated modules for which there are submodules which are not finitely generated. That's messed up, but it's true. And then item 2 here with theorem 5.8, let R be a principal ideal domain. If an R module is n generated, then any submodule of M is also n generated. So you can find a generating set with n things if you can find, And then at the end of this, he has Hilbert's basis theorem, which says that if a ring R is Noetherian, then so too is the polynomial ring R of X. And that's actually kind of a quite beautiful proof that you can look at here. Anyway, I'm going to start into modules over PIDs next time. And if we have opportunity, we'll come back to the Noetherian thing, where it gets interesting in the other arguments later. So we'll see. So it was more important to kind of go through some of these things today because they're not very sexy, let's say, but they're important. And so I'm going to try to give you guys homeworks that actually give you an opportunity to find for yourself like a counterexample to the thing. I gave you that list of what's not and what is. One of your homework problems, or actually problems, will be, giving examples which are for or against that. And so anyway, I'm thinking about your homework. I just haven't read it up yet. So thanks, guys.